Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. We are discussing about solid mechanics and materials subject. In previous session, we have discussed about slope and deflection of various beams. So how to calculate the slope and deflection of a beam when it is subjected to single load or various loads. So in this slope and deflection topic, we have discussed about the methods. So how many methods are there for calculating the slope and deflection of a beams? So already we have discussed about double integration method, and now in this session, in today's session, Macaulays method for slope and deflection. What is this method? How to apply this Macaulays method for slope and deflection of a different beams. So before going to enter the main topic, the student should be able to utilize the Maxwell's reciprocal theorem, double integration method, and moment area method for determining. They should know about this outcome. This is course outcome of this topic. So Maxwell's reciprocal theorem we will discuss later, and double integration method already over, and the moment area method also discussed. So first of all, we will see the slope and deflection of beams introduction. So what do you mean by slope? So it is angular shift at any point of the beam between no load condition and a loaded beam. So its value is different at different points on the length of the beam. So it is represented by I or theta. Its units are radians. So there is a maximum limit for slope for any loaded beam. So suppose I have taken this cantilever beam subjected to point load at its free end. The beam deflects like this. So in this is the angular shift at any point on the beam between no load condition and loaded beam condition. Its value is different at different points on the length of the beam. So represented with theta or I. So similarly, the deflection is the vertical shift of a point on the beam between no load condition and a loaded beam. Its value is different at different points on the length of the beam. It is represented by Y or delta. Its units are mm. So there is a limit for maximum deflection for any loaded beam. See, in this, the vertical shift of a point on the beam. So that is Y or delta. So what is the vertical shift? The distance, the deflection height. So there is a limit for maximum deflection for any loaded beam. So these are the two definition, slope and deflection, you should know before entering into the main topic. So methods for slope and deflection at a section. How do you calculate the slope and deflection at a section? So though there are many methods to find out the slope and deflection at a section in a loaded beam. And the following two methods are important from the subject point of view. One is double integration method, another one is Macaulays method. So already we have discussed about this double integration method. In this, first derive the one equation by using bending stress equation, and then integrate the equation. You will get first integration the slope, and again integrate the same equation. You will get deflection. So after substituting the C1 and C2, we will get final slope and deflection equations. Already we have discussed in the previous sessions. So it will be interesting to know that the first method is suitable for a single load, and whereas the second method is suitable for several loads. So the second method is the suitable for several loads, means the Macaulays method. This one is suitable for only single load. So we have derived slope and deflection formulas of a various beams when subjected to point load or UDL or variable load or eccentric load. But in this method, the Macaulays method, you can calculate several loads beams whenever the beam is subjected to point load and UDL and the combination of these two. So how to calculate, we will see. So Macaulays method for slope and deflection is a simply supported beam with eccentric point load. See here, consider a simply supported beam AB of length L and carrying an eccentric point load W at point C, so that the AC is equal to A and BC is equal to B, as shown in figure. These are the reaction forces RA and RB. RA is equal to W by L and RB is equal to W by L. Taking moments about A, WB into L, WB by L into and the RB is WA by L. So calculate RA and RB. So RA plus RB gives WB by L plus WA by L. So it means W into A plus B by L. So A plus B is nothing but L. So L get cancelled, you will get W. So that the upward forces RA plus RB is equal to W. So now calculate bending moment at any point in section AC at a distance x from A. So here from this take a section, any section, any point, distance is x. So take A as the origin. So the bending moment is negative bending moment minus W by L into x. So it's nothing minus RA into x. So the bending moment at any point in section CB at a distance x from A. So that is the bending moment, calculate here the minus WB into x by L plus here W into x minus C. So integrating the above equation, you will get EI into, so you can write this equation, bending moment is on mx from the bending stress equation. E by sigma by y is equal to m by I is equal to E by R. So already we have derived this equation. integrating the above equation. So integrate E I into d square y by dx square, integrate wx by L plus integrate w into x minus e. See, EI after integration you will get equation EI into dy by dx is equal to minus wb x square by 2L plus c1 plus w into x minus a whole square by 2. So integrating the above equation once again. So that is EI into y into minus wb x cube by 6L plus c1x. So first we will get first constant we will get from the first integration, and second constant we will get from the second equation C2. So w into x minus a whole cube by 6. Now calculate C1 and C2. Find C1 and C2 by using constraints or boundary conditions. We know that when x is equal to 0, then y is equal to 0. Substituting these values in equation 4 up to dotted line only. See, in this, substitute these values up to here only, up to dotted line, the x and y values. C2 is equal to 0. We also know that x is equal to L when y is equal to 0. X is equal to L, but then y is equal to 0. Substituting these values again in equation 4, and C2 is equal to 0. So in equation 4, first we will substitute x is equal to 0 and then y is equal to 0. Here x is equal to 0, y is equal to 0. Substitute here 0, 0 plus 0 plus C2. So here C2 is equal to 0. Similarly, when x is equal to L, then y is equal to 0. X is equal to L and y is equal to 0. So substitute x is equal to L, C2 already 0, x is equal to L and y is equal to 0. So 0 minus w L cube by 6L plus C1 L plus 0. So find out here C1. Substituting these values again in equation 4. Again we will get equation 4, we will get C1 value. C2 substitute and C1 will get WB by 6L into L square minus B square. So in equation minus WB by 6L into L cube plus C1L, W into L minus A cube by 6. So in this, minus W L square by 6. So L here get cancelled. WB L square by 6 plus C1L plus WB cube by 6. What is this? WB cube by 6. Why? Because L minus A, you can write L minus A is equal to B. Since L is equal to A plus B, as shown in figure. So that the C1 L is equal to WB small b L square by 6 plus W cube by 6 is equal to WB by 6 into L square minus B square. So C1 is equal to, so finally we'll get WB by 6L into L square minus B square. Now substituting this value of C1 in equation 3. So what is the equation 3? The 3 equation is A into dy by dx is equal to minus WB x square by 2L plus C1. So now substitute in this equation the C1 value. The C1 is WB by 6L into L square minus B square. So this is C1. So this is the required equation for slope at any point. We know that the slope is maximum at A or B. Substituting x is equal to 0 up to dotted line. Remembering here that C lies in a AC. As shown in a figure. The C point lies in AC. So after substituting the C1, the equation you will get EA into dy by dx is equal to minus WB x square by 2L plus W by 6L into L square minus B square plus W into x minus A whole square by 2. So you can write as fifth equation. Now EI into IA, you can write the dy by dx in terms of slope. That is theta or IA or theta A, IB or theta B. So W into B by 6L into L square minus B square. Here put x is equal to 0 up to dotted line. So the term will converted into 0. So now the theta at A, that is IA slope at point is equal to W by 6E I into L square minus B square. At B point, similarly, W into A by 6E I into L square minus A square. So substituting this value of C1 again in equation 4 and C2 is equal to 0. C2 0 and then the value of C1 substitute in equation 4. So this is the required equation for deflection at any point F, any point of a beam. For deflection in AC, consider the equation up to the dotted line only. The deflection point of AC is up to dotted line only need to consider. So in this, the deflection EI into Y is equal to minus WB into x cube by 6L plus WB x by 6L into L square minus B square WB x by 6L into L square minus B square minus X square. So y is equal to WB into x by 6 I into L into L square minus B square minus X square. So in this equation now, substitute the x values, you will get deflection for different points of a beam. Any point, by using this equation, you can calculate slope and deflection of a beam. So the Macaulays method may also be used for cantilever beams or for beams subjected to some movement. So this method is not only for simply supported beam, you can use for cantilever beams also. So this is the Macaulays method for slope and deflection. Next, one more theorem is there, that is Maxwell's reciprocal theorem. This theorem, sometimes also called Maxwell's reciprocal rule, is a technical relationship that equates two separate distortions in an elastic structure under load. So it can either be used to reduce the number of factors calculated in a given circumstance, or used as a check that the calculation has correctly predicted the equality of two separate distortions. The Maxwell's rule is one of the basic tools for structural engineering. For structural engineering, it is a basic tool. So this theorem is also called Maxwell's reciprocal rule. So it is a relationship between the equates two separate distortions in an elastic structure under load. So detailed explanation we will see. See here, shown beam, simply supported beam with some portion here overhang, and this one also overhang. So the load acting at its center. The deflection shown as in dotted lines. So unit load, and then the unit load, suppose acting at C, the deflection is like this, and CD, and suppose the unit load acting at D point, the deflection shown in this figure. So this the top sketch is a beam under unit load at C. So the delta xy is the deflection at point X due to unit load at point Y. So that is delta DC also shown, delta DC. It is a beam under unit load at C. The delta xy is the deflection at point X. Due to unit load at point Y. The lower sketch, the unit load is transferred to point D. So here first initially the unit load acting at C, the transfer to unit load D. So at this point, the Maxwell's theorem equates delta CD to delta DC. So a simple example of the general rule is illustrated in the diagram on the right. A beam is supported near either end. A unit load is applied in the center, for simplicity as an example at point C. The beam is not just deflected at the center, but all along its length. So let the deflection at a point D be delta DC. It gives deflection at delta C. So the theorem, the Maxwell's reciprocal theorem says that the deflection at D due to a unit load at C is the same as the deflection at C if a unit load were applied at D. So that is the main theorem. So that the main rule delta CD is equal to delta DC. The lower diagram illustrates the second illustration. So we have to do the explanation or proof for this delta CD is equal to delta DC. We will see in later. So in this, the point is the unit load is acting at C, the deflection is delta DC. Whereas shifted to D, the deflection is delta CD. So the both are equal. There is no change in deflection. So suppose this point is shifted to this one. So there is no change in deflection. So this is called the Maxwell's rule. So the beam is not deflected at the center, but all along its length. The Maxwell's reciprocal theorem does not just apply to beams, but any linear elastic body, including surfaces also. It doesn't just apply to displacements, but also to relations produced by torques. So it is derived relatively straightforwardly by examining the work done when two different forces are applied. The derivation part we will see. If a force F is applied against an elastic resistance, the Hooke's law says that the force of resistance increases linearly until it balances the applied force. Already you know the Hooke's law. The stress is directly proportional to strain. Within the elastic limit, you can write stress is equal to E into stress. So the stress increases, strain also increases. The force of resistance increases linearly until it balances the applied force. Suppose the final displacement is X. The work done against the increasing resistance is of force multiplied with X. On the other hand, if a force is moved a distance y, then the work done is F. So there is a further assumption that the distortion applied by a given force at a given point is independent of the existence of the other loads. There is a further assumption that the distortion applied by a given force at a given point is independent. So these basics are applied on the right to the situation of loads being applied in such sense. So first at C and then at D and then in the reverse order. So these basics are applied on the right to the situation of loads being applied in succession, first at C and then at B. Then in the reverse order, again D and C. So with a linear elastic system undergoing small distortions, the net result will not depend on the order in which the two loads are applied. So the argument on the right has been given for unit load, but any load can be taken under the assumptions. So now we will discuss about proof. By unit load method, the delta is equal to integral the bending moment at any point x due to external load, that is capital M. The small m is the bending moment at any point x due to unit load applied at the point where deflection is required. So this is external load. Due to the external load, the bending moment will get, that is m. The small m is the bending moment at point x due to unit load applied. at point require the deflection. So you can write integral capital M into small m dx by E into I. So let that mxa, the bending moment at point x, so that is small m into x, small x, at a, let small x be bending moment at any point x due to unit load at b, when unit load, the external load, is applied at A. So that is the bending moment capital M is equal to the bending moment at any point x due to unit load at A and B. So this is M is equal to the bending moment at A. So to find deflection at B due to unit load A, apply unit load at B, then the bending moment at this point is equal to B. So here, hence calculate deflection, find deflection B due to load A at point B. That's integral capital M into small m dx by A. So the capital M is equal to M x, small mx at point A bending moment, and small m mx b by EA into dx. Similarly, when unit load, that is external load, is applied at B, so that is M is equal to mx b. So again you can write the delta AB. So to find deflection at point B due to unit load at A, first calculate. When unit load, external load is applied at B, so again calculate, and to find the deflection at A due to unit load B, that is delta AB. Apply unit load at A and then M is equal to, small m is equal to mx A. So integral capital M into m dx by A is equal to small mb into m into xa by EA dx. So comparing these two, 1 and 2 equation, so we will get delta AB is equal to delta BA. So first equation, in equation delta BA is equal to integral mxa by EI into mxb dx is equal to integral mb x mbx mb into mx, integral mb into mxa by EA. Delta BA is equal to delta AB. XA XB by EA and XA by MB by EA. So both are comparing these two, the delta AB is equal to delta BA. This is the theorem result obtained as per the Maxwell's reciprocal theorem. So the theorem says the reciprocal, so actually this basics applied to the right to the situation of loads being applied in section. So this is the first first at C and then D and then in the reverse order. So both are equal. So the theorem says The reciprocal theorem says that the deflection at point D due to a unit load at C is the same as the deflection at point C if unit load were applied at D. So in our notation, CD is equal to DC, as shown in a figure. But in our theorem, in proof, we have taken AB. So like this, you need to derive this Maxwell's reciprocal theorem. And then this theorem apply for problem solving. So later we will discuss how to solve the problems on this Maxwell's reciprocal theorem and Macaulays method. So here I have taken references S. Ramamrutam. Title of the book is Strength of Materials. And R.K. Rajput. Title of the book is Strength of Materials. And R.K. Bansal. Title of the book is a textbook of Strength of Material. Lakshmi Publications publishers. And R.S. Kurmi and Gupta. Strength of Materials, the title of the book. So I have taken these references for this PPT. So you also refer any one textbook for further more clarification. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.